Okay, picture this. A world of data that is just a complete mess. You've got scattered notes, duplicate files everywhere, absolutely no security. It's total chaos. But what if? What if you could take all that chaos and turn it into something incredibly powerful, something clear? Well, that's exactly the journey we're on today. From that messy, disorganized pile of files to the elegant, structured world of the relational database.
So, let's break down the core problem we're trying to fix. Over on the left, you've got the old way of doing things, the file system. Honestly, think of it like having a dozen different notebooks for the same project. Your data is repeated, it's probably inconsistent, and security? Forget about it. But on the right, that's our hero, the Database Management System, or DBMS. This is like a super librarian for all your information. Everything is centralized, which means you can share it, you can trust it's consistent, and you can even recover it if things go wrong. It is a total game changer.
So, how does a DBMS actually create all this order from the chaos? Well, it doesn't just wing it. It uses a master plan, a kind of blueprint for organizing absolutely everything. And that plan? It's called the Relational Model. And this, right here, is where the real magic begins. The relational model is based on a surprisingly simple idea. We organize all of our data into tables. Now, the fancy name for these tables is relations. Each table has columns, which we call attributes. Things like name, age, or address. And it has rows, called tuples, where each row represents a single record. But here's the absolute golden rule. Every single row has to be unique. This simple, elegant structure is the foundation for pretty much every modern database you'll ever use.
And you know what? Let's see what that actually looks like. Forget the complex theory for a minute and just look at this simple, handwritten student table. You've got your column SID, S name, S address. Each row is a different, unique student. This simple grid, this is a relation. It's clean, it's organized, and it's the fundamental building block we use to turn that data chaos into data clarity.
Okay, so we have our nice, neat tables. That's a great start. But how do we keep them that way? How do we make sure the data going in is actually good data, that it stays accurate and reliable over time? For that, we're going to need some rules. We need some guardrails.
Which really brings us to this critical question, right? How do we physically stop someone from entering a student's marks as, say, a negative number, or leaving their roll number totally blank? How can we make the system enforce these common sense rules all by itself?
Well, the answer lies in something called integrity constraints. You can think of these as the official guardians of our data. They're rules that we define using SQL, the language of databases, to act as automated gatekeepers. And you can see a few of them listed here. Things like not null, unique, and the super important primary key. These guys are on duty 24/7, making sure that any data being entered is actually valid.
So let's zoom in on the most important guardian of them all, the primary key. A primary key's job is to uniquely identify every single row in a table. It's non-negotiable. For anyone who's been to college, think of your roll number. It was unique to you, right? That's exactly what a primary key does. It ensures every record has a one-of-a-kind identifier, which is absolutely crucial for preventing disasters like having two students with the same ID or billing a customer twice.
And here is how we actually put that guardian to work. It's not just a concept, it's code. When we're building our student table with SQL, we literally just tell the database, hey, this roll no column, that's the primary key. And that's it. From that moment on, the database itself will automatically reject any attempt to insert a duplicate roll number or leave it empty. The rule is set. The guardrail is officially up.
Now, if primary keys are the unique ID cards for our tables, then foreign keys are the bridges that connect them all together. A foreign key in one table basically points to the primary key of another table. This is how we can link, say, a student in our student table to the specific course they're enrolled in from a courses table. This is how we build a real interconnected web of data, not just a bunch of isolated lists.
All right, so our data is structured in nice tables and it's protected by our guardrails. What's the next logical step? Well, now we get to ask it questions. How do we pull out very specific pieces of information and start uncovering some really useful insights?
One of the most powerful ways to do this is with something called a subquery. It's exactly what it sounds like. It's a query inside of another query. Here's how it works. The inner query runs first, it finds some piece of information, and then it hands that result off to the outer query, which uses it to finish the job. It's kind of like asking a two-part question. First, find all the courses in the computer science department. And then, okay, great, now show me all the students who are enrolled in those specific courses.
Let's look at this query right here. The goal is to find all the employees whose salary is over $4,500. So, the inner query, our little scout, runs first. It goes out and finds all the employee IDs that meet that salary condition. Then, the outer query takes that list of IDs and says, "Perfect! Now go get me the full details for only these employees." It's just a super smart and efficient way to do really complex filtering.
Filtering is amazing, for sure. But sometimes we don't want a long list of individual records. Sometimes we just need the big picture. We need a single summary value that tells us the story at a glance. And for that, we have what are called aggregate functions. These are our power tools for doing calculations. You see them listed right here. Functions like count, sum, average, max, and min. They take an entire column of data as their input, and they spit out a single summary value. These are what let us calculate total sales, find the average score on a test, or spot the most expensive product in a snap. So let's see one in action. It's really simple. We're going to ask our product mart table a very direct question. What is the average cost of everything you sell? And the query to do that is clean, it's straightforward. Select AVG cost from product mart. And just like that, the database crunches all the numbers in that cost column and boom, it gives us back one single powerful answer, $77. I mean, that's the beauty of it right there, turning a whole list of data into one simple insight.
Okay, we have come a long way. We've structured our data, we've protected it with constraints, and we've learned how to ask it some really smart questions. For our final piece of the puzzle, let's look at how we can make the database even smarter by creating automated guardians that can enforce complex rules all by themselves.
And this incredible tool is called a trigger. You can think of a trigger as a special piece of code that you attach to a table, and it just sits there, waiting. It fires or runs automatically whenever a specific event happens, like a new row being inserted or an existing one being updated. It's basically an if this happens, then you do that rule that lives right inside your database, always watching and always ready to act.
Now check out this brilliant real-world example. If you follow the code, you'll see we're creating a trigger on a student table. This trigger is designed to run before any new student record is inserted. And what does it do? Its one job is to automatically calculate the total marks and the percentage based on the individual subject marks that were just entered. This is amazing, because it guarantees the calculations are always correct and it saves a ton of manual effort. It's automation at its absolute best.
So there you have it. From a total mess of chaotic files to perfectly structured relations, from setting up manual rules to building automated triggers, we've seen the entire journey of bringing order to data. The key thing to remember is that these aren't just abstract ideas. These are the real tools being used every single day to build the reliable, data-driven world that we live in. So the real question for you is, as data keeps exploding all around us, how are you going to structure it, protect it, and unlock its true power?